To start? Yeah. All right.
Get started.
Yeah. Okay. So yeah, if you want to, you can. All right. So yeah. Hi everyone. So yeah, it's a pleasure to host Ashrujit Ghoshal. He's a PhD student at the University of Washington, and he's going to be telling us about time-space trade-offs for short collisions in Merkle-Damgård and sponge hashing. So yeah, Ashrujit, take it off.
Hi everyone. Thanks for inviting me. This talk will be about some of my recent work on time-space trade-offs for short collisions in some popular iterative hashing mechanisms. And this is based on joint works with Coretti and Ilan Komargovsky. Hash functions are one of the most fundamental primitives in cryptography that have many different applications, and certain applications, for example, password hashing, require a hash function to handle different input lengths. And it is infeasible for us to construct a different hash function for each length. Therefore, we use the mechanism of iterative hashing, where we construct a variable input length hash function from a fixed input length primitive. And some popular examples of iterative hashing are the Merkle-Damgard hashing mechanism and the sponge hashing mechanism. Let's begin with a brief refresher of what Merkle-Damgard is. So the fixed input length primitive here is a compression function H, which takes as input two n-bit values and outputs an n-bit value. The hash of a message is defined with respect to a key k. The message is first padded appropriately and then broken up into blocks of n bits. And the hash is computed as follows. The first message block and the key k is used to evaluate h. The output and the second message block is then used to evaluate h again. And this continues till all the message blocks are consumed. The output of the final evaluation is the hash output. This construction is used in many of the hash functions that are regularly used in practice, like MD5, SHA-1, and SHA-2. One of the most basic properties that we require from any hash function is that of collision resistance, which entails that given a randomly sampled key, it must be hard for an adversary to find two distinct messages that hash to the same value. So we are interested in studying collision resistance for the Merkle-Damgard hashing mechanism. And the most usual approach to do that is to model this function h as a random oracle. And in fact, when we do that, we can show that with roughly t equals 2 power n by 2 queries, one can find collisions. And this is essentially what we call is a birthday style attack. Further, one can show that this attack is optimal. However, this function h is typically public, and an adversary might be able to invest a large amount of preprocessing on it. And in this setting of preprocessing adversaries, it turns out that this birthday style attacks are no longer optimal. This setting of preprocessing adversaries has actually been studied quite a bit in cryptography, starting from the seminal work of Hellman for function inversion, and in several other settings in subsequent works. And in particular, this captures the scenario, the class of non-uniform adversaries, something that we often care about in theoretical cryptography. So the auxiliary input random oracle model introduced by Unruh captures the power of these preprocessing adversaries against random oracles. So the collision resistance game in this model is defined as follows. There is an adversary A, which has two phases. The first phase, known as the preprocessing phase, has complete and unbounded access to the random oracle H. It can compute S bits of information, which it passes on to the second phase, which is known as the online phase. The online phase additionally gets as input a randomly sampled key. It can query the random oracle at most t times and wins if it can produce two messages which are distinct but have the same hash. We refer to such an adversary, A as an ST adversary, and define advantage parameterized by S and T as the maximum possible, maximum probability achieved by such an ST adversary in winning this game. Of course, one thing I'd like to remark here is when we model an adversary in this manner, we actually make it extremely powerful because the pre-processing phase has unbounded access to age, meaning that it could do highly non-trivial things. So any impossibility results or limitations that we prove in this model are very strong results. This advantage had been studied in prior work by Coretti et al. And in fact, they gave a tight characterization of this advantage, meaning that they gave an explicit attack that achieves advantage ST square over 2 power n, and also showed that in asymptotically that attack was optimal. However, the specific attack that they gave finds collisions that are of length roughly t, and for usual settings of parameters, this is like of the order of petabytes. And collisions these long are not really useful. Further, one can actually prove that finding collisions that are shorter are harder to find. And this was done in a work by Akshima et al., who showed that 2-block collisions are strictly harder to find compared to arbitrary length ones. Here, 2 in the subscripts denotes the advantage of an adversary in finding 2-block collisions. What I mean by a 2-block collision is the messages output by an adversary are both at most 2 blocks long. Further, in the work of Akshima et al., they gave an attack that achieves advantage which asymptotically looks like STB by 2 power n plus t square over 2 power n. And they put forward this conjecture, which they called the STB conjecture, which said that this attack was essentially optimal for all values of b 2 or more. But at the time, this conjecture was completely unresolved for any value of b, which is greater than 2, which is more than 2, till b much less than t. In a joint work with Ilan Komargotsky, we showed that this conjecture is true for all constant values of b and for certain other ranges of parameters. I'll tell you about the techniques involved in proving this later on in this talk. But before that, I'll tell you about some of the other results we have in time-space trade-offs for hash functions. So while I've been talking about Merkle-Damgard, and it is probably the most used iterative hashing mechanism, the latest hashing standard, SHA-3, is actually not based on Merkle-Damgard. In fact, in 2006, NIST started a competition after some attacks on hash functions based on Merkle-Damgard. And after nearly a decade, a construction known as Sketchak emerged as the winner. And importantly, it's based on a novel iterative hashing mechanism known as the Sponge construction. One immediate difference of Sponge compared to Merkle-Damgard is here the fundamental underlying primitive is a permutation instead of a function. Let me give you a very brief overview of how the Sponge construction works. It is parameterized by the bit rate R, that is the number of message bits per block and the capacity C. And the fundamental object is a permutation on R plus C bits. The hash of a message M is defined with respect to a key K. Again, the message is first padded appropriately broken up into blocks of length R bits. And the hash operation is computed as follows. An initial state consisting of R zeros followed by the key K is defined. The first message block is then XORed to the first R bits of the state, and the permutation evaluated on the result to compute the next state. And this continues till all the message blocks are consumed. The first R bits of the final state is returned as the hash output. Again, the question of collision resistance is something that we want to understand for the Sponge construction. And pictorially, this is what a collision looks like. The shaded part denotes the colliding output. So when studying collision resistance of the Sponge construction, typically what one does is model this ideal object, the pi, as a random permutation. And in this case, one can actually show that there's an attack with a minimum of 2 power r by 2 and 2 power c by 2 queries. This attack, the attack with 2 power r by 2 queries is again a birthday style one, where one evaluates the permutation with m and k for different choices of m until two evaluations have the same first bits, r bits of the output. On the other hand, the attack with 2 power c by 2 queries finds two messages where the last c bits of the evaluations match, and then one can actually turn it into a collision by cleverly choosing the second message block.
Yeah, by the way, there's a question on the chat. Someone's asking, is the permutation random and independent of the key k?
Yeah, the permutation doesn't depend on the key. Yeah, so it's a public random permutation. So again, the question of the security, the collision resistance of the sponge construction makes sense against preprocessing adversaries, and this model, the auxiliary input random permutation model, captures the power of such adversaries against random permutation. The collision resistance game in this model is very similar to what we saw for the case of random oracles. There's an adversary which has two phases. The preprocessing phase has unbounded access to the permutation, can compute S bits of preprocessing on it, gets a randomly sampled key in the online phase, and can make T queries to the permutation in its inverse. So here is one point of difference. Because it's a permutation, the adversary, and it's public, the adversary can query the permutation in both forward and inverse directions. And it wins if it can find a collision, and advantage is defined analogously. Pratik, very often. So prior work had a different work by Coretti et al. Had actually given a type characterization of this advantage. But again, there's the same issue that they run into. The attack that they gave finds collisions that are extremely long. And the question of finding short collisions had not been studied for any value of B. So in a joint work with Cody Freitag and Ilan Komar-Gotsky, we gave new attacks and proved limitations on best possible attacks for finding B block collisions in the sponge construction. In a little more detail, we gave a new attack for finding one block collision and a generic attack for finding collisions of length 2 or more, and proved limitations on finding 1 and 2 block collisions. So one key takeaway from our results was this ability to query this permutation in both forward and inverse direction actually leads to new attacks, analogs of which don't exist for Merkle-Damgård. But also at the same time, this makes our job much harder in proving limitations. So I gave you a brief overview of all the results we had. For the rest of the talk, I'd like to tell you a little bit about the techniques. So I'll cover two main techniques here. One where I'll show you an example of how we construct a new time-space trade-off attack. So I'll give the specific example of finding one block sponge collisions, and I'll also show you how we prove limitations with the example of proving this STB conjecture for Merkle-Damgard for constant values of B. So this is next. Yeah.
So you can think about CRHF as like this playing this game against the correlation intractability game for a specific binary relation, right? So the binary relation being finding two inputs, such that the outputs are the same.
Mm-hmm.
But so my question is there been any work or thought about like considering more expressive relations in the correlation intractability game? Like, what is the complexity of finding 3 collisions, or going to the other side, like for unary relations, which is basically useful for instantiating fusion?
So in this model, first, like, I'm not sure the question can be cast in this model where it makes sense. For example, like you can, so this is like keyed hash functions, right? So the question doesn't really make sense in this setting for non-keyed hash functions, because if the preprocessing phase, like if the online phase has to just find 2 colliding inputs, it can just put that collision in the S bits. The hardness is the key, the pre-processing phase does not get to see the key. The key is randomly sampled later.
Sure, you can define key versions of all of these different
Right.
correlation.
So yeah, so I'm not aware, like for example, no, so for 3 collisions, I'm not aware of results that study. Like, so by 3 collisions, I assume you mean like 3 inputs colliding. Right. No, I'm not aware of results like, yeah. Any other questions? Okay. So let's let me tell you about this new attack. So this is the theorem we prove. It's a very complicated looking bound, and I don't need you to read it. But I have it there for a reason that will be clear later. So let's give a little bit of context here. So the previously best known attack had advantage this quantity. So here this the attack that achieves this advantage s by 2 power c plus t squared by 2 power r is actually a fairly simple attack, what I call the trivial attack. So here, the first term appears because the adversary can simply remember collisions for s different keys. If the key got as input is among those s, it wins. So that's how the first term appears, and otherwise it does a birthday style attack. So that's like the most obvious thing you can do. For the case of Merkle-Damgard for 1 block collisions, it's actually the best you can do. But for the sponge construction, there are certain parameter regimes where the new attack that we have is exponentially better than this trivial attack, meaning that we have found a kind of scenario where the sponge construction is in some sense less secure than Merkle-Damgard. I'll denote this very complicated looking term by epsilon h squared, where epsilon h is the advantage for Hellman's attack for random function inversion. For those of you who are not familiar with it, I'll come back to this very soon. So taking a step back, we have to give an attack for finding 1 block collisions. More precisely, this is what we have to do. We need to come up with a strategy which, given a randomly sampled key k, finds 2 messages m and m prime, such that the evaluation of the permutation pi on mk and m prime k have the same first r bits in the output. As a first step towards the solution of this, let's make So I use the indices 1 and 2 to denote the first r bits and the last c bits of the state. So as a first step, let's actually make life a little more hard for ourselves and try to actually solve a harder problem. It'll soon be clear why I'm doing this. So I want to come up with a strategy that finds 2 messages m and m prime, such that the evaluation of the permutation on mk and m prime k are all zeros in the first r bits. So of course this satisfies the previous condition, but this is a stronger condition. Okay, let's take an alternate view of the situation. Let's define a function f, which has c bits inputs and outputs. What it does is it takes in a value x, it appends r zeros in front of x, evaluates the inverse of the permutation on it, and outputs the last c bits as its output. The important point about the function f is it does not depend on this key k, and we'll be actually leveraging this property and using existing space-time time-space trade-offs for random function inversion. This is how we'll do it. So I propose the following attack strategy. So given a randomly sampled key k, use function inversion to find 2 distinct inverses x and x prime. Having done that, compute m as the first r bits of the evaluation of the inverse of pi on r zeros followed by x, and m prime compute m prime similarly. Output the messages m and m prime. Okay, so why does this work? So if indeed x was an inverse of k under f, the last c bits of the evaluation of the inverse of pi on r zeros followed by x is k. And we know that by definition, the first r bits of this evaluation is m, meaning that the evaluation of pi on m and k produces all zeros in the first orbits. And we can prove the same thing for m prime, and we are done. Assuming that we know how to invert f on a random k and produce two distinct preimages. So, as I've referred to a couple of times, we'll use Hellman's function inversion. So, function inversion is a problem that has been studied in this scenario of preprocessing adversaries since a long time. The setting is as follows. There's a random function which has c bits inputs and outputs. There's an adversary A, which in its preprocessing phase gets unbounded access to the function, can compute s bits of information on it. In its online phase, it gets a uniformly sampled value from the image of the function, can make t queries to the function, and needs to output a preimage of its input. So Hellman gave an explicit attack which achieves this advantage, which was the complicated looking term from before. So the question is, can we just simply plug this in? Well, turns out that there are several technical challenges. Firstly, the function f, as defined here, it's not really a random function. Secondly, this randomly sampled value k might not even be in the image of the function. Finally, we need to find two distinct preimages, while Hellman's attack guarantees us to find one. I'll tell you very briefly about how we handle all of these challenges. So f is not a random function, but there have been works that have studied function inversion in more general cases where the function is not a random one. There's one by Fiat and Naur, but it turns out if you plug in Fiat and Naur's analysis, the bounds that you end up getting is actually worse than the trivial attack. So what we observe is that f is close enough for a random function so that Hellman's analysis can be adapted for it to work. Secondly, the challenge, the randomly sampled key might not be in the image of the function. So first off, in order to solve this, one might observe that we can show that a constant fraction of the codomain has at least two preimages for a random function. Does that suffice? Well, it's on its own, it's not enough, because Hellman's attack might actually fail for this constant fraction. So we need to say something stronger. So what we did was we analyzed Hellman's attack, and we showed that for a fixed value in the codomain, the attack succeeds with probability that is proportional to the number of inverses the particular value has. Finally, we need to find two distinct preimages, while Hellman's attack gives us one. Of course, the first idea anyone would have here is, okay, run the algorithm twice with different randomness and hope it spits out two different preimages. But of course, it's not immediately clear that it works. So we analyze Hellman's attack further and show that, in fact, it finds a uniform preimage among all the preimages. And that suffices for our needs. And in fact, that's what makes the bound square. Of course, there are all of these points are very subtle, and there are lots of details that I swept under the rug. I invite you to read our paper for all those details. So are there any questions? So having given you a taste of how to actually construct new attacks, I'll next give you a sketch of how we actually prove limitations on the best possible time-space trade-offs. So I'll be looking at our proof of the HTB conjecture for Merkle-Damgard for constant values of p. So just to refresh, this is the setting. There's a preprocessing adversary that in the preprocessing phase has unbounded access to the random oracle, computes s bits of preprocessing on it. The online phase gets a uniformly randomly sampled key, can make t queries to the random oracle, and has to output a collision. The collision has to be B blocks long. So this is the result that we prove. Again, it's a complicated looking expression, but for constant values of p, we essentially, this bound shows that this STB attack is essentially optimal. Okay, so the proof of this theorem goes through this framework known as the multi-instance framework, recently discovered concurrently in the works of Chung et al. And Akshima et al., but inspired by an old work by Impaliazzo and Kabanets in proving constructive Chernoff bounds. So the setting is as follows. There's this following game. Here there are u is a parameter, which I'll tell you how we set later. There are u different keys sampled uniformly at random. An adversary gets as input the first key along with some degenerated bytes, say the all zero string. It can query the random oracle at t points and has to output a collision.
Sorry, there was a question about, I guess, previous slides. So they're asking whether send is a bit better. Does the key k have to be larger than the input length x? I'm not sure which.
No, the key k has to be larger than. No, there's.
Oh, it's a generic question.
No, no. No, that you want to handle arbitrary length inputs for hash functions. So you actually don't want such conditions. Okay, so there are u uniformly random keys. So here the online phase of the adversary gets some degenerated bytes like the all zero string here. The first key, it can query the random oracle at t points and has to output a collision. Then it is run similarly on all the keys successively. The adversary A2 wins if for all the keys it actually finds B block collisions. And here's the key point of the framework. There's a lemma that tells us that if we can upper bound the advantage of the adversary in winning the multi-instance game, this directly leads us to an upper bound on the advantage of an ST adversary in the game that we are interested in. So essentially, we want to prove this upper bound on epsilon. I'm putting this expression out here. It's complicated, but later on you'll see the reason why it's on there. Okay, so our job is to now upper bound the advantage of an adversary in winning the multi-instance game, and the technique we'll use here is a very standard combinatorial technique, which is often referred to as a compression argument. The idea behind a compression argument is extremely simple. It essentially says that for a randomly sampled value in a set X, it's very unlikely that one can compress it to something that is of size much smaller than log of size of X. So here, just to spell it out a little bit more, suppose there's some set X and there's some encoding algorithm that takes a value of from the set X and spits out a value in some set Y, and there's a decoding algorithm which decodes the value from set Y to set X, and even the encoding and the decoding algorithm share some common randomness. The probability that this decoding would be correct is basically at most the ratio of the size of Y by the size of X. It's a very of course the proof of this lemma is a fairly simple counting argument, but in cryptography this has been used to prove it's been used in many settings to prove many different lower bounds. So this was the setting that we were in, and what we will do here to upper bound the advantage of an adversary in winning this game is we will actually give a strategy to compress the random oracle H along with this set of U randomly sampled keys, and this compression will work whenever the adversary wins. and that would allow us to use the compression lemma to prove an upper bound on the advantage of this adversary winning. Okay, so before, so I'll actually give you an example of how, I'll go through an example of how we do this, but we'll make this simplifying assumption that when running on a particular key, the adversary only queries the random oracle prefixed by that key. Of course, this assumption is a very unreasonable one, and we'll get rid of it eventually. So, assuming that, this is our encoding strategy. So, when the adversary gets the first key as input, we add the key to our encoding. Whenever the adversary makes a query, we add the answer of the query to the encoding until the first time when running on a particular key, there's a collision. That is, the Zj equals Zi from such that Zi was the response for some earlier query. In that case, instead of storing J, we remove it and we store a tuple j comma I in the encoding. And we do this, we run the adversary on all the keys and do this for all of them. Finally, after running it on all the keys, we add the evaluations of the random oracle on all the values that were not queried by the adversary in lexicographical order of the input. So this is how decoding will work. Since the encoding contains all the keys, the decoding algorithm would run the adversary on the first key, answer its queries using the answers that are present in encoding. And for example, but how would it detect values that have been removed? So here, since the index j is present in the last list here, it knows that it has to answer this query, the answer it gave for the ith query. And this is how it will run the adversary on all the inputs. And finally, fill in the unqueried entries of the random oracle using the last part of the list here. So here is a very hand-wavy sketch of how encoding and decoding would work. And whenever, and one can show that whenever the adversary wins, so one can actually compress for every value of the key, there's a savings of n minus 2 log p bits, giving a total savings of u times n minus 2 log t bits. So here the savings of n bit happens because for every key we are omitting one answer, and instead remembering those two indices j comma I, and each index is log t bits, and plugging this in directly gives us an epsilon, which is actually better than what we want. But of course, this is all under this assumption that we made that when running on a particular key, the adversary only queries the random oracle prefixed by that key. So we have to work much harder to remove this assumption. Towards this goal, let's define a query graph. So, which is initially empty before the adversary is run. When the adversary is first run in the multi-instance game on the key K1, when it makes a query on x1, y1 and gets z1 as the answer, we add two nodes, x1 and z1 in the query graph, and add an edge y1 from x1 to z1, and we keep drawing the graph across all the runs of the adversary. Here, I note that the adversary might repeat queries across different runs. For a single run, we might assume that it does not because it can simply remember answers, but across different runs, queries might be repeated. And also, additionally, we'll assume that in order to, if the adversary outputs a particular message as its collision, it has made all the queries it needs to compute the Merkle-Damgård evaluation of both the messages. So, assuming this, let's look at how do B-block collisions actually look like in this query graph. So the structure of the collision is something like this. It actually reminded us of a mouse, so we called it the mouse structure and named the different parts of the collision with different body part names. Of course, there might be slight variation in how a collision exactly looks like. It might be that the whole loop of the body is a self loop, there might not be a tail, and so on. So one thing that we do is for a particular key ki, there might be multiple of these structures, like the adversary might end up finding multiple collisions, but we isolate one of them arbitrarily, and we call that the mouse structure for that particular key. Okay, so the second thing we do is we categorize types of queries. We say that a query is a new query if it is being made for the first time. So we can assume without loss of generality that there are no queries that are repeated in a single run of the adversary, because it can just remember the answers. So therefore, a new query, if a query was not made in the previous run of the adversary, it's a new query. And queries that are not new are repeated queries. And we further categorize it into two kinds. One is repeated mouse queries. That is, some query is a repeated query and it had appeared in some earlier mouse structure. And repeated non-mouse queries are all the other queries uncategorized. So from now on, I'll make a different assumption that before running the adversary on a particular key, the random oracle had not been queried prefixed by that key. So this is, I claim that this is a much more reasonable assumption, and I'll justify it very soon. And this in particular implies that every mouse structure has a new query, because the mouse structure for every key has to contain the key itself. And since it's not been queried before, the structure has to have a new query. So now we can classify mouse structure into different types. For example, they have some colliding new queries. The body of the structure is a self loop, and so on. We can exhaustively classify them into these types. And the goal is to save a minimum of these number of bits for all these mouse structure to get that complicated looking bound that I showed you. Because then once we get this amount of savings, adding it all up and applying the compression lemma gives us our desired bound. So I'll give you an example of two cases of how we make these savings. One of them is an easier case, and the one will highlight the main challenges. Okay, before that, I made this assumption that before running the adversary on a particular key, the adversary has not queried the random oracle prefixed by that key. Why is this assumption reasonable? Well, it turns out that if the adversary has queried on that key, we don't need to save on anything, and we can just save on the key itself. Recall that we were compressing the random oracles along with the set of keys. So in this case, what we would do is we would omit the key from the encoding and instead store the index of the query where the key was queried as a prefix. And that's more than delta that we want to save. And that suffices. Okay, so let's see an example where of a mouse structure where it's easy to save. So say the mouse structure has a new query Q2 whose answer was like the input of some query Q1, which is a repeated mouse query. That is, it's present in so it's a query that was present in the mouse structure of some earlier key. So here our strategy to compress would be to omit the answer of the query Q2 and instead remember the indices of Q1 and Q2. So I claim that this is the savings we get. The n bits we save is from omitting the answers of Q2. We need log t bits to remember the index of Q2. So there are Q2 is a new query. There are at most t queries when running on the solid ki. So we can encode it in log t bits. And the index of Q1. So there are a mouse structure that roughly has b queries, and there are u mouse structures in total. So Q1 must be one of these UB queries, and we can encode its index in log of UB bits. And this suffices for our needs. Let me show you an example of a case that is much harder to handle. Say the mouse structure has a repeated mouse query Q1 and there's a new query Q2, but they are not consecutive like in the previous case, and there are a series of repeated non-mouse queries between them. So extending our previous strategy, what we would need to do here is we would additionally need to store a path back from Q2 to Q1, specifically this path here. Zooming in a little bit, one way to remember this path back is for every node in the path, remember which edge to take back. Of course, the number of edges to take back might be a lot. So first, let's consider the case where there are no large multi-collisions. So we define that there is no large multi-collision when essentially the in degrees of all the nodes is at most log u. So if there are no large multi-collisions, we can encode the path using these many bits, where the first term comes from encoding the number of edges in the path, and the second term is the maximum value required to encode which edge to take back. And it turns out that this again gives us enough savings, but of course, assuming that there are no large multi-collisions. So finally, we need to address this. What if there are large multi-collisions? Our main idea would be to save from the large multi-collision itself. Specifically, we say that a multi-collision is a M multi-collision if there are M queries that have the same answer. So in this case, we'll save the answer of, we'll only remember in our encoding, we'll just remember the answer of the first of these queries and only the indices of the rest of the M-1 queries. So here we get a savings of these many bits. So the first term is from omitting the answer of M-1 queries, and the second term is the cost we pay for remembering the set of indices of the other queries. When M is at least log u, it turns out that we actually get enough savings, and that suffices for us. Of course, there are several other cases, and even in these cases, I omitted some of the details, and I'd be happy to talk about it offline or refer you to our paper. So finally, to conclude, there are two main takeaways from all these works on space-time trade-offs. So for the Merkle-Damgard construction, this STB conjecture is actually true for a large number of parameters. In fact, after our work, there was a follow-up work by Akshima, Guo, and Liu, which showed that this conjecture is actually true for all values of st square less than 2 power n. And for Sponge, it's interesting that inverse queries are actually useful for new kind of attacks that actually make it slightly less secure than the Merkle-Damgard construction. And there are, we actually show an attack which is provably not present for Merkle-Damgard that works as Sponge. There are several open problems. There are limitations that we prove for the Sponge case are only for b equals 1 and 2, so everything else is open there. And our bounds for even b equals 1 and 2 are not tight. For Merkle-Damgard, of course, there's this remaining range of parameters for which you need to prove this STB conjecture. Both of our papers are on ePrint. Thank you. I'd be happy to take any questions.
Any questions? No.
So in your compression argument, what was the need for storing the unqueried part of the edge? I guess that's because you want to come up with a encoding and you want to define correctness of encoding and decoding over all possible x.
Yeah, so basically
you try to relax it, like if you don't store the unqueried edge, would you try to relax the requirements on the correctness in the compression argument and probably get better parameters?
No, so the thing is the compression argument works for like when you have a fixed random object. So when you're not storing the unqueried part, like you're letting somehow the adversary choose which parts of H you are storing, right? So you're having some adversarial control, and it's no longer so the distribution of what you're like encoding is no longer uniform. So you need to, going back, to the compression slide here. So here, like the probability is over all x. So like this set, like script x is fixed.
Yeah, that's what I'm saying, right?
Yeah.
I mean, if you fix the script x,
yeah,
this is the best you can get.
Yeah.
But and because the script x is fixed, you have to add the unqueried edge.
Right.
But I'm saying that let's not add the unqueried edge. Can you then come up with a relevant notion of a compression argument or this lemma that might give you better parameters?
So I'm not.
Even in that case, there is compression going on. Even if you remove the anti edge, there is still some non-trivial compression, right?
So I'm not thought a lot about it, but like just as an intuitive exercise, like suppose you have a random oracle, right? You might be able to find structure in some part of it. Like if you draw out the graph of a random, say the random oracle has same domain and range, so you can define a graph, a functional graph of it, right? And maybe there is some part of the graph that has a very good amount of structure, and then you can of course compress that part. The point is you cannot compress the whole thing together. So that this is an analog to the adversary. Maybe the adversary, you can run the adversary to achieve compression on some part of the random oracle. But for the compression argument to go through, you need to compress the whole thing. Yeah.
Okay, no, let's thank Ashrujit again. Oh, there's another question.
Okay, I can have.
Yeah.
Am I just reading?
Yeah, I can. So just to clarify my previous question, I meant to ask if k has to be larger than x, where x is not the whole input, but the block of the input that you feed along with the k, with k to the first permutation of the sponge construction, which is all zeros initially.
Oh no, so basically, yeah, I had those two parameters C and R in my construction. No, there's no our results actually are parameterized by C and R. So yeah, there does not need to be any fixed relation for C and R.
All right, thank you. Guys, still recording.